In the previous videos, we discussed the III-V absorber materials and their use in multi-junction devices. We will now look at some special applications of III-V solar cells, starting with concentrated PV. In this video, we will focus entirely on the optics of the lenses used for concentrating light. The learning objectives for this video are to recap Snell's law of refraction that was introduced in the first course of this solar energy program. We will then look at some refractive lenses and the Fresnel lens in particular. Finally, we will look at some reflective mirrors that can also be used for concentrated photovoltaic applications. Let's first look at Snell's law of refraction. This law states that the angle of transmission depends on the angle of incidence and the refractive indices of both materials. It also states that the ratio of the sines of the angles of incidence and transmission is equal to the ratio of the refractive indices of the media. Increasing the difference between the refractive indices will increase the angle in which the light beam is refracted. The angle of reflection, however, simply equals the angle of incidence, regardless of the refractive indices of the two media. So let's put Snell's law into practice. We will follow a number of beams emitted from the blue point source. The point source is inside a medium with a refractive index of 1.5, for example glass, and light is emitted into a medium with a refractive index of 1, such as air, for example. The first beam arrives at the interface under normal incidence. According to Snell's law, this beam is transmitted under normal incidence as well. At an angle of incidence of 20 degrees, the beam is refracted at the angle of 30.9 degrees. A fraction of the intensity of the beam is reflected. A beam with an angle of incidence of 35 degrees is refracted at an angle of 59.4 degrees. This shows that as the angle of incidence decreases, the angle of refraction increases even more strongly. When the light beam is incident on the angle of 41.8 degrees, the beam will propagate perpendicular to the plane of incidence. This angle of incidence for these particular refractive indices is known as the critical angle. If the direction of the beam is reversed, the beam will travel the same path. This reversibility means that a flat material will not focus any light. If we take, for example, this flat surface with a refractive index of 1.7 and a finite thickness. Light incident under an angle of 40 degrees will be refracted at an angle of 22 degrees. At the second interface, the beam will again be refracted, back to an angle of 40 degrees. The beam therefore only undergoes a horizontal shift. For that reason, concentrated lenses are spherical. The shown lens is spherical on one side. The spherical lens is designed such that the perpendicularly incident light is focused onto a focal point at some distance from the lens. In reality, a lens has some optical aberrations. This means that not all perpendicular incident light will be concentrated into a single focal point. For instance, any spherical lens will have a spherical aberration. The rays incident closer to the top and the bottom of the lens end up converging at a shorter distance from the lens. The refractive index of a material is wavelength dependent. Generally speaking, the refractive index of the types of glass used for lenses decreases with increasing wavelength. For short wavelength blue light, the glass will therefore have a larger refractive index mismatch with air than for high wavelength red light. This means that blue light will be refracted more and have a focal point closer to the lens. This is known as a chromatic aberration. These optical aberrations pose some serious challenges for lenses in imaging devices, such as cameras and beamers, where a concentrated focal point is essential for creating a sharp image. For concentrated PV, the light needs to be focused onto a solar cell with a certain area. Even though the optical aberrations have to be considered during the lens design, the lenses used for CPV have a much larger tolerance. As we can see, this lens is designed such that all perpendicularly incident light is focused onto a solar cell. This has two important implications. On the normal operation, both direct and diffuse light will be incident on the lens. The diffuse light will be incident from all angles. For most of the angles, the light will not be refracted onto the solar cell. CPV therefore only makes use of the direct light. Most of the diffuse light is not used. The second implication is that the lens and solar cell have to face the sun. Otherwise, the sun's direct radiation will not be perpendicularly incident. This means that concentrated photovoltaics requires a tracking system that adjusts the direction of the CPV system during the day. We'll discuss the tracking system in more detail in the next video. For CPV applications, normal lenses would have to be very thick. These lenses would be relatively expensive and have a relatively high optical absorption. Therefore, Fresnel lenses are generally used. For Fresnel lenses, the lens is collapsed back to zero thickness at a number of points. This figure illustrates how this is achieved. The lens is divided into a number of grooves. The red areas basically represent excess material which is removed. The resulting Fresnel lens has the same curvature, but is much thinner, resulting in negligible absorption losses. Since the Fresnel lens can also be used to disperse a concentrated source of light, one of the most successful applications is the one in lighthouses. An alternative to refractive lenses is the use of reflective lenses, or mirrors. A reflective surface with a parabolic shape will focus the rays at some distance parallel to the parabola's axis. To that end, large parabolic dishes, such as in this picture, can be used. Alternatively, parabolic troughs can be used like this one. Please note that this picture shows a solar thermal system, but the same principle applies to CPV. Now in summary, we discussed Snell's law of refraction and applied it to see how spherical lenses concentrate light onto a focal point. We discussed the spherical and chromatic aberrations that occur for lenses in reality and how lenses only concentrate direct light and therefore require solar tracking. Finally, we discussed the Fresnel lens and the use of mirrors for PV systems. In the next video, we will discuss the effect of light concentration on solar cells.